Well, good evening, everyone, and welcome to the February meeting of the Highlands Astronomical Society. We live in strange times. That being the case, I want to reassure long-term HAS members that they have not slipped back 2 years in time. Eric is still your chairman. As meeting organizers, we've been dealing with a technical issue over this webinar. So this evening, Eric will be doing the club news, and I am backing him up as chairman for the night. Which leads me nicely onto how the evening will pan out. After this brief introduction, we are going to go into Pauline's talk on the subject of Juno at Jupiter. I shall introduce Pauline in a moment. Then Rona will pose your questions for Pauline to answer before I give a vote of thanks. Finally, Eric pops up to lead us through the club news and also members' astrophotography results. As I close the meeting after that, we introduce a new feature tonight. As this webinar meeting ends, you will be given the opportunity in the chat channel to click on a link which will take you over to another non-webinar Zoom meeting at which we can have a blether with whoever many people decide to jump over and join us. It's a feature new to us, but Sigma do it regularly and it works well. We hope that you will join us. There isn't going to be a Zoom briefing tonight. We reckon that you will have got the hang of it by now. However, if you do run into problems, put a question into the Q&A channel, and our webinar host, Rich Oakley, or our co-host, Mick O'Donnell, will hopefully sort you out. Alternatively, you could click on the hand icon at the bottom of your Zoom screen, and that will also get their attention. So, now to our speaker, Pauline. What can I say? A HAS member for more years than she would probably care to remember. She was our chairman for 7 years and still serves on the committee. She is an absolute stalwart. As many of you will know, Pauline is an excellent speaker who gives a talk to us every year, and I'm really looking forward to her talk tonight. I confess that as part of our contingency arrangements, I hold a copy of her presentation slides here, and I've already had a sneaky look at them. They're great. So without further ado, may I introduce to you Pauline and her talk, Juno at Jupiter.
Thank you very much, Paul. I'm just going to share my screen. Okay. Well, good evening, everyone. I'm going to tell you about Jupiter from Juno's perspective. Juno is a spacecraft in orbit around Jupiter at the moment. But in Roman mythology, she was also Jupiter's wife, and only she could see through the clouds that Jupiter surrounded himself in so that no one could see what he was up to. The Juno spacecraft is designed to look beneath the clouds to help us understand the planet's structure and history. And you'll see that a lot of things scientists thought they knew about the king of the planets are actually wrong. We're all familiar with what Jupiter looks like from the outside. It has a multicolored coat with magnificent autumnal hues, smeared into bands by opposing winds, creating complex and exquisite patterns with whirls and swirls of cyclonic features, towering storms within and between the belts and zones. What we see, however, is just the surface, and Jupiter's interior is a little bit more of a mystery. Does it really have a core? And how deeply do the belts and zones extend into the planet? Much of what we have learnt comes from the many spacecraft that have flown past this gigantic planet. but nothing beats an orbiter for gathering information. In the 1990s, Galileo mined a treasure trove of knowledge, but it still left us wondering, especially when the Galilean probe released into the atmosphere did not give the information scientists were expecting. Juno is also an orbiter, but powered differently. Let me get my laser pointer. Until this mission, all spacecraft to Jupiter and beyond have been powered by an RTG. That's a radioisotope thermal electric generator. And that's these black things that you can see here. Now, as you can see, Juno has 3 solar panels, making it the first spacecraft to travel as far as Jupiter under solar power. Each panel measures 2.7 by 8.9 meters, so they're pretty big. They have hinged segments that were folded for launch and deployed soon after. Now, Jupiter is 778 million kilometers from the sun. So solar power is not something that would generally be considered at this distance. Juno's solar panels will only receive 4% of the sunlight and generate just 486 watts of power instead of the 12 to 14 kilowatts of power that they would on Earth. But with a global shortage of plutonium-238 and with advances in solar cell technology, it actually became economically viable to use solar panels to provide Juno with power so far from the sun. Juno was launched in 2011 and arrived at Jupiter in 2016. And once it was captured by the gas giant, it moved into an elliptical orbit, which took it over the poles. And this is the first time a spacecraft has ever investigated a planet using a polar orbit instead of the usual equatorial one. After performing 2 53.5-day orbits, there was going to be a main engine burn to take it into the 14-day science orbit. Unfortunately, there appeared to be a problem with the helium valves in Juno's main engine. And so to avoid an engine misfire and possible disaster, it was decided the spacecraft should remain in its initial orbit for the rest of the mission, providing a big burst of data every 53 days. Juno's orbit takes it to 4,200 kilometers at its closest and 8.1 million kilometers at its furthest. And that provides the opportunity to investigate the far reaches of the Jovian magnetosphere, the bubble of magnetic fields surrounding Jupiter. And Jupiter's magnetic field is the strongest and largest in the solar system, with its magnetotail extending all the way to Saturn's orbit. One of the main challenges of the mission was the amount of time Juno would have to spend inside Jupiter's radiation belts, which are pretty lethal. The longer orbit reduces exposure, and by taking Juno through a gap in the radiation envelope here, emissions are kept to a minimum. To further protect Juno, it has a 1 centimeter thick titanium wall, which helps to shield the electronics. So far, this has worked. And after 4.5 years, the instruments are still functioning, including the camera, which they expect to be first to fail. There are 8 instruments on board, as well as a camera for education and public outreach. And I'm sure that I read somewhere that they weren't going to include a camera, but there was such an outcry that they did. And it's turned out to be really important, because it not only helps put the science that they're doing into perspective, but it also engages the public, which is just as valuable. In addition to their instruments, the spacecraft carries 3 mini Lego figures representing Jupiter, Juno, and Galileo. The instruments hope to answer some of the biggest questions astronomers have, and Jupiter's primary science goal is to understand how, when, and where Jupiter formed, as this is directly related to the conditions in the early solar system, which of course led to the formation of our own planet. And this means that Juno will measure the amount of water and ammonia in the deep atmosphere, investigate whether or not there is a solid planetary core and how big it is. It will map Jupiter's intense magnetic field and observe the planet's aurora. Jupiter's most distinctive feature is its stripes, and these are made up of alternating dark belts and light zones. Both are made up of ammonia, but the light-coloured zones are upwellings of fresh ammonia clouds, which form ice crystals as they cool, and that's why they're white. And then the dark-coloured belts correspond to descending gas, which increase in temperature as they dive deep into the atmosphere. The heat turns the ammonia ice into a gas once more, and along with other gases, probably sulfur and phosphorus, as well as exposure to ultraviolet light, gives the belts their dark coloration. And the area near the poles appears to be bluer in color. Could be due to less exposure to ultraviolet light, but nobody is quite sure. Now, the belts and zones could be thought of as large-scale convection currents, similar to those that we have in Earth's atmosphere, where warm air rises and cool air sinks. And then between the belts and zones are powerful winds known as jets, which are caused by Jupiter's fast rotation. It only takes just under 10 hours to complete one revolution. And the faster the rotation, the more likely the winds are to move directly east and west. As heat rises from Jupiter's interior, and as the planet rotates, hundreds of vortices are formed within the bands and the fast-moving jets. These vortices are the circular rotating structures that we think of as storms. More than 90% that are larger than 2,000 kilometers are anticyclones or high-pressure areas. They generally last between 1 and 3 years, although the biggest ones can last a lot longer, while the smaller ones disappear more quickly. This one, you can see, moves in an anti-clockwise direction, and it's in the southern hemisphere, which is why it's considered an anticyclone. And then you get the reverse happening in the northern hemisphere. The anticyclones usually appear as white ovals, but not always. This is the little red spot that's in between colours at the moment. They can move sideways, but tend not to cross from one band to the other. And they often merge when they approach one another. Indeed, most anticyclones are formed from the merger of smaller ones. However, they've never been observed in the equatorial region of Jupiter, as they are considered to be unstable here. The cyclones are the low pressure areas and are always located in the dark belts and jets. Now, if you have a look at this one, it looks rather like an eye. But with this, in this photograph, you can see it's the same picture, but it's been processed in such a way to show the height differences in the clouds. And this gives the image depth. So this is an actual cyclone on Jupiter. Quite scary. They tend to be smaller, but not always. The cyclones are also darker, often anyway, sometimes very dark. And this picture reminds me of abalone shell. And they tend to be more irregular. There are also several large filamentary regions which appear to rotate like a cyclone, and you can see them just here. And these are images of Jupiter taken as Juno passes over. And you can see the cyclone here gradually disappearing from view. We've got the little red spot, and we have got the orange band, which is the north-north temperate belt. So you can see that even planetary scientists have poor imagination in the same way that astronomers tend to have a poor imagination when naming things. Now this image shows those strange filamentary clouds. So you can see it here. And if you look at this bit in particular, you'll notice that that's what we're looking at here now. We have a look at this image. It's been processed in such a way to show movement. And just look at the way these vortices turn. They're absolutely extraordinary. And then the way the gas just moves around. It's beautiful, and it's something that you could look at for a long time. Perhaps the biggest anticyclone of all is, of course, Jupiter's Great Red Spot. It has probably existed for more than 350 years, and it's shrinking. In the 19th century, it was well over 2 Earths wide. In 1979, when Voyager 1 flew past, it was nearly twice Earth's diameter. But now, measured by Juno, it's just 1.3 Earths wide, or 16,000 kilometers. It also changes in color and ranges from light pink to deep crimson, with various colors in between. The amateur astronomers processing the images tend to make the color a little richer than it is, perhaps, although its true color shows it to be fairly bright at the moment. And this image shows the clouds racing anti-clockwise around the spot's perimeter with wind speeds of over 400 kilometers an hour, far greater than any storm on Earth. And these dark bits that you can see, well, these are holes into the cloud. And the Great Red Spot is an area of atmosphere which rises high above the cloud deck by perhaps 8 kilometers, where it cools, releasing more heat than anywhere else on Jupiter, thus appearing a little bit colder on top when measured by Juno's microwave instrument. And I'll talk about this a little bit more in a moment. So Jupiter's microwave instrument measures the temperature of the Great Red Spot as it descends surprisingly deeply into the atmosphere. And they think it could be 300 to 350 kilometers deep, whereas a tropical cyclone on Earth is only about 15 kilometers from top to bottom. What you're looking at are slices through the atmosphere. So this is your visible layer, and this is the temperature of that visible layer at these different, well, right at the top, and then you have these slices at different depths. The darker the image, or the darker the color, the cooler it is, because remember, it's losing heat as it rises upwards. And by the time you get right the way down here, the lighter colors show it to be extremely hot. And it's the difference in the heat from deep below to the cooler surface that drives strong winds that surround the edges of the spot. And as it moves through Jupiter's atmosphere, it creates these beautiful turbulent flows, as you can see here. And as I've said before, they remind me of Viennetta ice cream. There are 3 cloud layers found at the top of Jupiter's atmosphere. We've got ammonia ice clouds, ammonium hydrosulfide clouds, and the water ice cloud layer. Also, they think, because they're not absolutely sure it's there, although it should be, because of the thunderstorms that occur. And one of the objectives of the microwave radiometer is to find this layer. Now, this is the instrument which looks at the heat emitted by Jupiter in the form of microwaves. And because water and ammonia gas absorb microwaves, it's possible to map their distribution in the atmosphere. So this is the track that Juno takes, and this is the track of the bit of the atmosphere that it's measuring. And that's the same track there. As Juno spins, it's able to look at Jupiter from different angles, which means that by using 6 different channels, and that's number 5 in there, it's possible to see 6 different depths. It's a bit like a CT scan where you can see slices of the planet. It was assumed that ammonia would be uniformly mixed under the cloud layers, but the big surprise was that that doesn't seem to be the case, and you can see that because it's really quite blobby here. If we look at this in a bigger picture, you can see the distribution of ammonia a little better. The brighter the color, the greater the abundance of ammonia. The darker colors indicate much less ammonia. This is the equator. And as you can see, just to the north side of the equatorial zone is a very light blob that extends downwards. And this can be found all the way around Jupiter like a ring. And next to it, in what would be the north equatorial belt, is a place where there seems to be a depletion of ammonia. That's the dark colors. And you can see depletion here and here and here. And it's really below this layer here that they assumed that the atmosphere would be well mixed. But as you can see, it's not. In fact, they even found that the depletion and abundance of ammonia doesn't even match up with the zones and belts. So these are the slices through the atmosphere. This is the track of the microwave radiometer. And you can see here the abundance of ammonia just to the edge of the equatorial zone. And then the depletion of ammonia is right at the edge of the belt here. And again here, almost within where you get the jet streams. So this didn't quite make sense. And in fact, they measured the amount of ammonia. As they measured the amount of ammonia present in the atmosphere, they found that most of it seemed to be missing. And scientists were at a loss to explain why this should be until they realized that storms probably have a part to play. Now, various spacecraft have seen lightning flashes in Jupiter's atmosphere, and scientists have assumed that the lightning was generated in the same way as Earth's, occurring only in thunderstorms where water exists as ice, liquid, and gas. Moisture-laden air from the water clouds 45 to 65 kilometers below the top of the visible clouds is pushed strongly upwards by heat rising from below to form these tall convective columns, some of them quite possibly 100 kilometers high. They are always associated with powerful lightning, confirmed by Juno's radio waves. And they always find that lightning is itself a marker of convection. And the thunderstorms look like bright clumpy clouds around 1,000 kilometers in size within the cyclonic areas of the belts, and especially within the strong jet streams. However, some of the lightning flashes seen on Jupiter's dark side during close flybys of Juno showed a different kind of lightning. This was smaller and shallower and originated at much higher altitudes in Jupiter's atmosphere. In other words, it was higher than the water cloud layer, which shouldn't have been possible. And what scientists think may be happening is that the powerful thunderstorms occurring in the water cloud layer fling water ice high into the atmosphere, well above the water clouds. At these altitudes, temperatures are extremely low, below -88 degrees centigrade, which is too cold for pure liquid water to exist. But this is where the water ice comes into contact with clouds of ammonia, which acts like an antifreeze and melts the water ice, thus forming ammonia water clouds. This liquid rains downwards, collides with upgoing water ice crystals, which electrifies the clouds, producing the high altitude electrical discharges known as shallow lightning. In this way, some of the ammonia is removed from the atmosphere. And these white clouds that you've probably seen quite a bit now, are thought to be the tops of violent thunderstorms, which are responsible for the shallow lightning. And you'll see a lot of them in these dark belts and jet streams. However, the water ammonia rain was not enough to explain all the emitting ammonia. But if there was something like hailstones, more ammonia could be used up, and this fitted well with the observation. It's thought that these hailstones, called mushballs, consist of 2/3 water and 1/3 ammonia. And layers of water ammonia slushy ice, seen here in green, are formed with a thicker water ice crust. And this is created as the mushball moves up and down in Jupiter's thunderclouds, in the same way that hail forms in Earth's thunderclouds. And as the mushball is moving up and down, collecting its icy coat, it starts off this, or it produces this shallow lightning. And as the mushballs increase in size, they gradually deplete this area in both ammonia and water. And they eventually get so heavy that they fall deep into the atmosphere. And as the temperature increases, they melt and evaporate. Now, when ammonia and water form mushballs, they are invisible to Juno's microwave instrument because they become a solid. And as soon as they evaporate, they become gases again, which means that they can be seen by the microwave instrument once more. So the ammonia is not actually missing, but it's in disguise. It's wrapped itself in ice, it's become a solid. And that's why it appears depleted in large areas of the atmosphere. The formation of mushballs and subsequent depletion of ammonia and water might explain another mystery, which has been ongoing for about 25 years. And this came about when data from the Galilean probe suggested there was less water in Jupiter's atmosphere than expected. And the probe also didn't pass through the predicted water clouds, although as it penetrated the atmosphere further, the amount of water appeared to be increasing. So think about how those mushballs are forming. Scientists thought the probe had entered one of Jupiter's relatively rare dry hotspots in the belt just north of the equator. Results from Juno's microwave instrument indicate that the entire northern equatorial belt is generally a very dry region, with plenty of storms and presumably mushballs. Now the equator is quite different. Juno found that water here makes up 0.25% of all the molecules in the atmosphere, which is nearly 3 times the amount found in the sun. Although of course the sun doesn't have liquid water, it's just in the form of hydrogen and oxygen. And of course, the microwave instrument also found an abundance of ammonia here. In addition, there's no lightning or thunderstorms, and as there are no updrafts of moisture-laden air, so no small-scale convection. So this area seems to hold on to its water and ammonia that seems to be depleted everywhere else. And once water has been measured in other areas of Jupiter's atmosphere, scientists should have a better idea of how it's represented across this gas giant. And that's important for Jupiter's formation theories. Now, unusually, there appears to be more lightning in the polar regions than elsewhere. And that's quite different to Earth, where we have most of our lightning occurring in the equatorial regions. But lightning also, or in fact particularly, occurs in structures called folded filamentary regions. That's these wonderful areas here. And these seem to be areas where a lot of moist convection occurs, which fuel the thunderstorms that produce lightning. The detail of Jupiter's banded atmosphere is just incredible. But what about the poles, which hadn't been seen before Juno arrived? Well, they turn out to be completely different to the Jupiter we usually see. The belts and zones break down at around 64 to 68 degrees north and south, and the high latitudes become rather chaotic in shape. And this is where we find the folded filamentary regions. This account describes them perfectly as clusters of unorganized filamentary structures, streams of air that resemble giant tangled strings. At the poles, there are a number of cyclones, each thousands of kilometers across, surrounding an even larger central cyclone. They're hard to see in visible light, but in this close-up of the North Pole, using both JunoCam and the infrared auroral mapper, it's possible to make out 8 cyclones, 1, 2, 3, 4, 5, 6, 7, 8, surrounding a central cyclone. These are about 4,000 to 4,600 kilometers in size. So they are huge. Infrared wavelengths show them up nicely. And what we're looking at is heat radiating from them as Jupiter gradually cools down. And it's this heat that may be driving these storms. In this image, we can see depth. And the white here, the very bright colors indicate height. And this is the South Pole. And here we have got 5 cyclones surrounding a central cyclone. And these are even bigger, 5,600 to 7,000 kilometers in diameter. And this image also shows depth. Now, they seem stable, long-lived, and mostly unchanging, although at the South Pole last year, or was it the year before, I think, a small cyclone, a 6th cyclone, a lot smaller, made an appearance, but it didn't last very long before its older siblings kicked it out. And this whale shape here is actually the outline of America, North America, but it's just to give an indication of how big these cyclones are. And this is an outline of Texas. Now, they all spin in the same direction and are so close together that their spiral arms come into contact with adjacent cyclones. And yet, despite the winds between them moving in different directions, if you think about it, look at the way the winds goes in the same direction, but at this point, they're now moving in the opposite way. And yet, they don't become messy at the edges. They don't seem to change, but remain fairly distinct. No one's quite sure why they don't just merge, especially considering that Saturn has a single cyclonic vortex at its pole. However, computer models suggest that stability will depend on how deep they are, but particularly on these anticyclone rings. We just about make out that they are moving in this direction, which is opposite to these little cyclones in the middle. And it seems that the strength of these winds, or the speed of these winds, has to be absolutely perfect. Otherwise, computer models show that the cyclones either come closer together or they push each other apart. Let's now delve deeper into Jupiter's atmosphere, with the belts and the zones. Now, are they limited to a shallow atmospheric layer, or do they penetrate deeply into the interior? The data has shown that they are probably at least 3,000 kilometers deep. And to work this out, scientists measured Jupiter's gravity field with incredible accuracy. And this was only possible because of Juno's polar orbit. And I'm quite sure that they're going to send all spacecraft into polar orbits after this, or all spacecraft visiting planets, that is. And the gravity field is determined by looking at how strongly Jupiter's gravity pulls on the spacecraft as it orbits the giant planet. The tiny changes in the spacecraft's speed can cause subtle shifts in radio signals sent back to Earth, and these are the Doppler shifts. This builds up a picture of how density is distributed inside a planet, as this might not be evenly spread out. One area could be denser than the other, and this is certainly what they do for rocky planets. But Jupiter is a fluid planet. It consists of either gas or some sort of liquid. There's no solid surface. Therefore, the planet should have the same gravity field in both hemispheres. So it was a surprise when measurements by Juno showed that this wasn't the case. Scientists believe this asymmetry may be due to the differences in the jet streams between each hemisphere. You'll notice that some winds are stronger than others. And that's what these arrows here are showing you. Now, the strongest jet has wind speeds of up to 140 meters a second. This is at latitude 23 degrees north, but there is not a similar jet in the southern hemisphere. So that's your 20 degrees latitude. That's your 0 line of longitude, whereas this jet is much weaker than this one, and it's going in the opposite direction. Now, in order to affect the density inside Jupiter enough to give the difference in the gravity fields between the north and south hemispheres, the jets, and thus the belts and zones, must extend deeply into the planet, because the deeper they go, the more mass they contain. And if the wind speeds are different, this creates a mass imbalance between the hemispheres, which Juno's instruments can detect. If the belts and zones didn't extend as far, then Juno wouldn't be able to pick up this mass imbalance. In fact, the bands are so deep, it's quite astonishing, because it means that the weather layer of Jupiter is absolutely massive. From the top of the atmosphere to its base 3,000 kilometers below, this layer accounts for about 1% of the planet's total mass, and that's huge. By comparison, Earth's entire atmosphere makes up less than 1/1,000,000th of its mass. So Jupiter has an enormous region rotating in these separate east-west bands. And further evidence suggesting the bands have to extend deeply comes from the discovery of particular molecules that scientists believe must come from great depths where temperatures are very high, suggesting that the cloud top bands really are just the tip of the iceberg. Now, beneath this weather layer at the base of the belts and zones, Juno found that Jupiter rotates like a solid body, except of course it's not actually a solid, but a fluid mix of hydrogen and helium. But at this depth, it's extremely hot, with pressures around 100,000 times that of Earth's atmosphere. And the hydrogen gas is now so compressed that it can become ionized. This is where electrons are knocked off the atoms. The resulting free-moving electrons can apparently cause enough electrical conductivity to generate a magnetic field, which then controls the movement of the belts and zones 3,000 kilometers down, in effect freezing the flow, and the planet becomes rigid, dragging the atmosphere around with it to rotate at a constant speed. This doesn't happen closer to the surface because temperatures and pressures are lower, so the hydrogen behaves quite normally. And the belts and zones that we see at the surface are simply due to convection and the way the planet rotates. Now, temperatures and pressures continue to increase as we move even deeper into Jupiter. Eventually, the gaseous hydrogen and helium will transform into liquid hydrogen and helium. And then at depths where pressure is around 2 million bars, that's 2 million times the atmospheric pressure on Earth at sea level, the liquid hydrogen is compressed so much that it changes into metallic hydrogen. This is a liquid metal, perhaps most similar to mercury. And this is a phase of hydrogen where electrons are free to roam and, just as with the ionized hydrogen, can conduct electricity and generate a magnetic field, but a much, much stronger one. And then below the metallic hydrogen is an assumed core, but no one was sure. There are two main theories of how Jupiter formed. One theory will result in there being no core, the other that it would be small and compact, and the answer should determine which theory is correct. So, by looking at the gravity data once again, the Doppler shift will produce different signals depending on the size and density of the core, and will be different again if no core is present. What they found was a large fuzzy core with no definite boundary, and possibly spreading over half of Jupiter's diameter. Now, you can think of a core as an area in the center of a planet where there is a concentration of heavy elements, that is, those above carbon. It seems that there were heavy elements not just in the center of Jupiter, and that's all these gray blobby bits here, but also extending into the liquid metallic hydrogen. There may be a tiny dense core at the very center, but the rest of the core appears to be partially dissolved in the metallic hydrogen. Now, there are a number of possible reasons as to why Jupiter has a diluted core, but the model that perhaps fits the Juno data best is the one involving a giant impact with a large planetary embryo. This would have shattered Jupiter's primordial compact core, then mixed material from the core with the metallic hydrogen, enriching it with heavy elements. Eventually, even the outer layers over billions of years would also end up with some heavy elements. Now, this is actually consistent with the findings of the Galilean probe. Thus, a diluted core helps to explain the structure of the planets seen today. But the scenario is not well understood, so it's just a theory. Heat escaping from the interior due to the planet cooling down, as well as Jupiter's rapid rotation, stirs the metallic hydrogen, creating convection currents, which then give rise to a dynamo, and thus to a magnetic field. It is this substance, the liquid metallic hydrogen, that fills most of Jupiter, and as you have seen, may merge with the core. The metallic hydrogen is thought to be the source of the planet's enormous magnetic field. But as you may have realized from something I said earlier, there is a layer of hydrogen gas at the base of the belts and zones 3,000 kilometers down, which is thought to become ionized and carry an electric current. And this may be contributing to the magnetic field. So how do we find out? Well, Juno has twin magnetometers which measure the magnetic field about 60 times a second, while the entire spacecraft spins twice each minute. And it does this along all of the polar orbits, gradually mapping the field. This can help to understand what the metallic hydrogen is doing inside and how it might be generating the magnetic field. Earth's magnetic field is mainly dipolar, and that means it looks as though it's got a bar magnet shoved down the middle of it. Jupiter's magnetic field is predominantly dipolar, at least from a distance. And this is where you have magnetic field lines coming out of the North Pole and then going back into the South Pole. So very similar to the way Earth looks. And this is what you would expect from a fluid planet. But the close polar approaches made by Juno have allowed it to get a much more accurate picture. And you've guessed it, the result was totally unexpected. Instead of a dipole field, what you see is a strong and relatively narrow positive band around 45 degrees north. So you can see that here. And this is where the magnetic field lines appear to come out of Jupiter. And what they do is to go back in at this isolated, intense, opposite polarity spot that they've called the Great Blue Spot. And there it is there. And then some of the other magnetic field lines come out of this reddish area, this positive area, and go back in at the South Pole, so the South Polar region. And this variation, these patchy features, and especially the Great Blue Spot, suggests that at least part of the magnetic field must have been generated closer to the surface, a bit like Uranus and Neptune, where it's thought there is an outer fluid layer that conducts electrical currents to produce their dynamos and therefore their magnetic fields. So basically, Jupiter's magnetic field resembles Earth's dipole field in the southern hemisphere and the more complex fields of Uranus and Neptune in the northern hemisphere. And this makes Jupiter's magnetic field unique in the solar system. One explanation for this lopsided magnetic field is the existence of the diluted core. It may be layered, creating two separate dynamo regions inside Jupiter. One in the metallic hydrogen layer, perhaps producing the magnetic field which looks like a dipole, and another one which is shallower, perhaps at the base of the belts and zones, maybe manifesting in the Great Blue Spot. But again, nobody knows, and all of this is just speculation. Now, where you have a magnetic field, you can create an aurora, and high energy particles go zipping down the magnetic field lines and collide with the atoms in the atmosphere, releasing energy in the form of colored light. On Earth, the solar wind generates our aurora, but on Jupiter, this seems to be much less important, with other factors coming into play, because the gas giant's aurora is permanent, although its intensity varies from day to day. This is Io's footprint, just to point this out. It is hundreds of times more energetic than the aurora on Earth, with most of its energy showing up in ultraviolet light and the X-ray part of the electromagnetic spectrum. As Jupiter spins, so does its magnetic field, sweeping through the electrically charged gas or plasma that fills its magnetosphere, much of which comes from the volcanoes on its little moon, Io. And these volcanoes produce sulfur and oxygen, which end up in this, what's called the Io plasma torus. They become ions, and gradually they infuse the rest of Jupiter's magnetosphere. And then they zoom down Jupiter's magnetic field lines into the atmosphere and cause the main auroral oval. And within the oval, we've got the so-called footprint. So here's Io, Ganymede, and Europa. And these footprints of the Galilean moons are due to their interaction with the plasma in the magnetosphere. Now, a very close look by Juno discovered that Io leaves a pattern of these vortices swirling off the footprint's tail and visible for hundreds of kilometers. And then a little bit further on, the tail splits into two. And Ganymede, apparently, has two footprints. Now, Earth's most intense aurorae involve strong electrical potentials, and it's these which accelerate charged particles along magnetic field lines towards the poles with increased energy. And then when they collide with the atoms and molecules in the atmosphere, the energy absorbed and released is highly energetic and produces very bright and structured aurorae. Jupiter's aurora is the brightest in the solar system, so planetary scientists assumed it was produced by the same process that creates Earth's strongest aurorae. But although Juno observed electrical potentials, that's these here, and that these electrical potentials were 10 to 30 times larger than those found on Earth, this didn't always produce an intense aurora. So they realized there must also be another process at work, especially since the aurora turned out to be 100 times stronger than Earth's, not just 10 to 30 times stronger. What scientists think may be happening is that the electrical potentials generated become so strong that they become unstable, forming waves in the plasma in the magnetosphere. By interacting with thousands of different waves, some of the charged particles can gain a huge amount of energy to drive Jupiter's powerful aurorae. So think of waves in the ocean. Think of them all coming together and producing one enormous wave. And that's the sort of thing that these scientists are thinking of. Juno also found that some of the auroral light emissions seem to be produced by electrons streaming out of Jupiter's atmosphere near the poles, whereas others did the usual thing by streaming in. But this then created a huge electrical potential of around 1 million volts. And this helped ionize and excite molecular hydrogen, causing ultraviolet emissions, but could also explain the enormous energy seen in some X-ray aurora. And Jupiter's aurora behaves differently between the poles, especially in X-rays, whereas Earth's poles mirror each other very closely. Finally, JunoCam is the camera that has been taking the remarkable photographs you've been seeing. Most of them have been enhanced, which is why they look so dramatic. But this brings out detail to aid the scientists and also to provide us with some utterly beautiful creations and artistic designs. And this is a citizen science camera for the purposes of public engagement, in that amateur astronomers choose the targets, download the images, and then process them. Although it's not one of the science instruments, it is very useful for the science team. So far, Juno has changed the way scientists think about Jupiter, turning much of what they thought on its head. We desperately need more information, and fortunately, Juno's mission has been extended again. It had been extended to July of this year, but now it's been extended until September 2025, when surely there will be a few more answers by then. So what has Juno learnt? And I'm just going to put this along a little bit because it tends to be a bit blurry initially. So Juno has discovered that the atmosphere is not well mixed below the surface. A lot of the ammonia is missing and could be due to disguising itself as mush balls. More water has been found than expected, but only at the equator so far, although it too appears depleted in some areas. The poles look completely different to the rest of Jupiter. The belts and zones extend to about 3,000 kilometers down, much further than was believed, beneath which the planet rotates as a solid body. There is a core, but it is unexpectedly diffuse. The magnetic field is lumpy and does not have the dipole appearance that had been found by spacecraft from further away, that appears very different when looked at close to. The dynamo which drives Jupiter's magnetic field may be closer to the surface in some places and could in part be driven by ionized gas just beneath the belts and zones. And the strongest aurorae is caused by a different process to the one that causes the strongest aurorae on Earth. And some of Jupiter's aurorae are caused by charged particles coming out of Jupiter's atmosphere. All this information will go towards understanding how, when, and where Jupiter formed, providing a window into the earliest times of the solar system. Jupiter continues to astonish. The incredible photographs of its atmosphere reveal a world of sophisticated patterns woven into elegant beauty, all the while obscuring the intricate nature of its interior, reluctant to give up its secrets. And yet, when it does, it is still able to spring surprises after all this time. Thank you.
Lovely, well done. Rona, would you like to take us through Q&A now?
Yes, indeed. What wonderful pictures, Pauline. I particularly like the three-dimensional cloud. You can see the layers.
I know, it's beautiful, beautiful.
From Richard, what, in your opinion, was the greatest discovery of Juno's visit?
Oh, gosh.
There's so many.
Exactly, an awful lot. Quite possibly the poles, which they didn't expect, although they did know that there was the central cyclone at Saturn's poles. I think maybe the core, the fact that it's diffuse, it's not what they thought at all. Either there was going to be none, or it was going to be small and compact. So I think that was a big surprise, and will quite possibly affect how Jupiter formed. Even though they think this is due to a giant impact, they're not sure. There are various other possibilities. So I don't know. Even the fact that the belts and zones extend so deeply into the planet. But there were so many things. I mean, they thought they had Jupiter pretty well wrapped up. Maybe just a few things that they didn't quite understand, a few little troubling aspects. And then they discovered that there's a whole load of stuff. And now they're going to have to go back to think all over again. So yeah, that's a difficult one.
And of course, it's not yet finished. They've got another couple of years, so it could be more stuff.
Which is absolutely brilliant. It's necessary. And I think this is one of the reasons why they extended the mission. And the fact that everything is still in good working order, because they expected everything to be destroyed by now, particularly the camera, because of the radiation. And yet everything is still going strong.
There's a question about how do they protect Juno from the magnetic or the radiation fields?
It's got this 1 centimeter thick titanium shield for the electronics. And they're just very careful about where Juno's orbit goes. So there seems to be a gap which they can put Juno through, but the radiation belts aren't quite as strong as they were expecting. I think they thought they were going to be much closer into the planet, but it's not quite so bad. But Juno's orbit is very gradually changing.
Mm-hmm.
And it's going to take it into those radiation belts that little bit more. So it will come a point when the instruments will start to be damaged. But that's basically how they do it. And of course, the 53-day orbit instead of the 14-day science orbit has turned out to be quite fortuitous, because it gets Juno away from the radiation belts for a fair bit of time. And therefore, all these things help to protect Juno.
Is there a plan towards the end of the mission to push the spacecraft into the radiation belts more? Because they've got nothing to lose.
Well, yeah, I don't think they'll go into the radiation belts, but they'll dive bomb it into Jupiter,
mm-hmm.
because they don't want it damaging any of the moons.
Mm-hmm.
But the other nice thing about the extended mission is that they will manage a flyby of Io, Europa, and Ganymede. I don't think they're going to manage Callisto. So that's pretty good going. So that's be useful. And that'll be as a preliminary thing before the JUICE mission, which will be the next one to Jupiter.
Mm-hmm.
And that's the one that's going to be looking at the icy moons, Europa and Ganymede in particular.
There was a question about the Jupiter's moons from Darren Moody. Has Juno given us any new information about Jupiter's moons? But not yet.
It discovered another volcano on Io.
Mm-hmm.
And I think there was something about radiation and stuff
Mm-hmm.
for coming from Io, but
Mm-hmm.
nothing really startling that I can remember reading. But then I was looking more for stuff about Jupiter, so I could well have missed it.
A question from Eric. Has Juno ever picked up when comets or asteroids have crashed into Jupiter's atmosphere? Has it done anything to the cloud structure?
I don't think Juno has seen anything going into the atmosphere.
Mm-hmm.
So it won't have seen anything happening there, unless it's just one of these things that they've not said an awful lot about. Finding the information, as usual, was quite difficult. Even the stuff they put onto the websites, it doesn't include everything.
Mm-hmm.
A lot of the science journalists weren't, the more reading I did, the more I realized that they weren't quite understanding the findings. They were taking quotes from scientists out of context. And even the scientists they didn't explain things terribly well. And you'll be left thinking, well, why is that happening? How does this occur? And it was very annoying. In fact, one of the slides I had to erase part of because the scientist had labeled it wrongly. And I only realized that when I was looking through various other slides. I thought, for goodness sake, that's not good.
Okay, Rona, I think we'll stop
Thank
it
you,
there,
Pauline.
please.
You're welcome.
Hello again. Well, you know, Pauline, I've been interested in astronomy for a number of years now, and I reckon I've learned a bit about it. But you never fail but to come up with a stream of factoids that I just didn't know. What a splendid talk. Interesting, detailed and knowledgeable, and presented in your usual clear and lucid fashion. Well done, and thank you ever so much.
Thank you very much, Paul. Now we can see you.
Yes, I know. This host of mine, he wouldn't let me in.
Oh.
So, thank you, Pauline. Onward now to the club news. And in a moment, I shall hand on to Eric. But just to say before I do, though, if you think of any questions that you would like to ask about the club as he goes through his bit, pop them into the Q&A channel and we'll take a look at them at the end of Eric's piece. So, over to you, Eric.
Good evening, everyone. I'm Eric Walker, and I'm the chair of Highlands Astronomical Society. Pauline, that was a fantastic talk. And because Pauline gave that talk, I'm honoured to have been able to take over this slot for the evening, and I just hope I can do it justice. I've certainly enjoyed preparing for it, so we'll see what we now have. I'm going to start off by giving you a little bit of club news, a little bit about targets, and the most enjoyable bit for me, which is showing and presenting the astrophotographs that club members and affiliated club members have been obtaining through the month. So, first of all, some great news. Our membership has risen to 61, and that was from a start of 42 at the beginning of this membership year. That was last April. So that's all great news considering all the troubles and trials we've gone through this year. I think that's a fantastic situation we're in. All our monthly club meetings and our live observing webcast recordings, they're all now on YouTube, and they are all available for paid up members. I saw a question on the Q&As, and I think it was from Aberdeen Astronomical Society. Yes, you guys are affiliated members, part of the North of Scotland Amateur Astronomy Association, so we'll make sure that you get the link to be able to view this presentation and pick up all the things that you missed in that wonderful in-depth talk. Normally, if you're not a member, you'd not be able to access the live webcast or live meetings recordings on YouTube for 3 or 4 months. So that's a member's benefit for our club. We decided our last club meeting that all our monthly club meetings will be via Zoom until and including December 2021. The speaker programme is very nearly finalised, and we'll get that published and out to you shortly. And as Paul mentioned earlier, we're going to start having club meeting blethers on Zoom after the main event. And the first one will be tonight. We are working on our ways to be able to hold face-to-face club member get-togethers once the COVID restrictions are relaxed throughout the rest of this year, hopefully anyway. I'd like to remind you again, please join our WhatsApp groups. There is Nebulous News, that's for event alerts, and it's especially for short notice alerts such as Aurora or a live observing webcast session that's about to happen in the next hour or two. And Noctilucent Clouds will probably be a feature in the summer, so please consider joining that one. There's also Cosmic Convos, and that's there for anyone to talk about anything at all astronomy related. Someone might want a bit of assistance in observing or whatever. It's for absolutely anything. If you contact our membership secretary, Lorraine Shepherd, she'll get you online with WhatsApp. So now I'm going to start off showing our new Highland MAN all-sky camera. MAN means meteors, aurora, and noctilucent clouds. You can view it at this URL shown on the slide. Note that it's available to all the public. It's not just for HAAS members. So if you want to have a look at the sky tonight, just take a note of the link and paste it into your browser and it will take you straight there. Now, the targets for the month, I've been lazy and I've simply regurgitated Pauline's ones. I've used the all sky camera to show you what to look for. Last month, Pauline pointed you to the winter hexagon and the winter triangle. Now, in this all sky camera image, north is to the right edge of this image and south is to the left edge. East is up to the top and west is to the bottom. This is your winter hexagon area that you want to look at. It's actually just great trying to find the winter hexagon itself. That area of sky it covers is much bigger than this fisheye lens image gives you. It's huge, huge area. But when you find it, look at it with your naked eye and look at it with binoculars or a small telescope if you have one. There is an abundance of objects in that area. It's just an absolutely wonderful area. And if you want to see what's in that area to look at, have a relook at our YouTube recording of last month's meeting or Stargazy Pie that you were sent out by email from Pauline. Now here's the first astro pic for tonight. This was a star trail image that was captured on the 5th and 6th of January, one of the few clear nights and moonless nights that we got. What you're able to see here are lots of different stars. There's different colours in the stars. There's different intensities of the lines reflecting their different relative brightnesses. This is the pole star in the middle here. So it's nearly dead center of the stars revolving around it, but not quite. The thick line that you see here, that will be Mars. If you go onto the All Sky Image page on the website, there's a little image, a little menu image, and you can click on the star trail images every night. You don't always get a good star trail like this, but when you do, it is something wonderful. Now, in this image, I managed to capture the International Space Station for the first time just a couple of nights ago. And this is a time sequence of the event. What you want to do is look very early on and you'll see the International Space Station as it streaks past this side of the image. There's also a few bright satellites as well, which streak across this area here. So keep your eye out for them. They come after the space station. Twilight at dawn or dusk is a great time to look at the all-sky camera. The satellites that cross our sky are at their most reflective then. So here we go. I'm going to kick off the time lapse. Be very quick to look at it because you'll see the streak up here early on. So here goes. And there it goes. You see that one? Very quick. And if you keep on looking, you'll see a couple of satellites streak. There you go. There'll be another couple in just a second. 1, 2. There you go. There are all kinds of flashes and streaks in this short image. But as I say, go to the website and you'll see for yourself. I've actually got hooked on this all sky camera. I have to walk away from it sometimes, but there are some magnificent images on it. Now, this one was fantastic. This was also on the night of the 5th and 6th of January, and this captured an aurora. It was a very short aurora, about 20-25 minutes long, and I have got it here in this time lapse. I want you to look at this side. Remember, this is north for me. I'm in Conham Bridge, so looking north means I'm looking just over Ben Wyvis. What you'll see the sky will brighten at this side, And then you'll see the dancers. You'll see rays dancing, the aurora rays dancing. Okay, so I'm going to kick this off. Just keep your eye on the right-hand side of the image. Sky's brightening and the rays dancing. You can even see a little bit of colour in there. Isn't that fantastic? Absolutely fantastic. I'm going to actually play that again for you in case you missed it. Keep watching the right-hand side and you'll see the aurora form and the rays dancing off it. Wow. I was so pleased when I saw that. Here's some stills of it. And what you'll see are the rays dancing off the top of the auroral arc. Now, I got another one. This aurora was a bit longer, and the time lapse has allowed me to capture what I call the dynamics of an aurora. What you'll see in this one, this was on the 11th, the night of the 11th, 12th of January, you'll see a brightening of the sky in the right. If you can think of an aurora as a battery charging up, it charges up and it charges up and it starts to release some energy. It gets brighter and brighter. It eventually forms a very distinct arch. And in this time lapse, you'll see that as a bright line in the right side of the image. And then it charges up some more. And I'll show you, I'll talk you through it as I'm doing it. So here we go. This is the area you want to be looking at. Okay, it charges up, it brightens, and it brightens until you see a very distinct line. That line would be the auroral arch if you were looking at it. And the dancers form and the dancers dance off it for a short time. It starts to settle down. The battery is continually charging up, but it's also giving out light. It's charging up and giving out light, but it's very stable. And then it charges up once more, big charge, and it starts to dance again, and the dancers start to come off, and it dances and dances, and of course, typical, as it starts to dance, the normal clouds come in, and that's the end of the aurora observing for that night. But a wonderful thing to see, and just some of the things you can do with this all-sky camera. And now, going back to some of the images I captured throughout the development of this aurora. So it's been captured from the roof of my house on the all-sky camera, but I went out, and this is just at the back of my house in a field, and this was early on, as you saw the aurora just starting to brighten on the all-sky camera. Here is the arc, or the arch, just forming over Ben Wyvis, looking towards Dingwall. I then went to Colbokie, and this was at the time that the auroral arch formed. It was its most distinct. That's when you saw the distinct line on the all-sky camera, and there is the arch. I then went to Ross County Football Club training grounds, just next to them in Dingwall, overlooking the Cromarty Firth in the Eventon Tane direction. And you can see this is the stable, as the aurora is very stable, and it was stable like that for a good hour and a half or so. There's the plough, if you want to get your bearings, in the pole star up here. Bonny pictures. Now, I just want to show you this. This is the app I now use. It's called the Glendale Sky Aurora app. And one of the bits that's in it is a section called the substorm strength data. And if you look at the graph of this, when these peaks drop dramatically. That's when the aurora is charging up and giving out its energy at a tremendous rate. It just almost erupts, and that corresponds, those peaks correspond exactly with when you saw the periods of dancing light. I 100% recommend this app. This was developed by Andy Gray from the Isle of Skye. It's free and it is superb. The link to it is here, so if you want to take a note of it, or I can include it in the chat section. It is absolutely superb. You can Google it to get it. It's not an app as such. It is, in actual fact, it's really a mini website, but it's completely free. One of the reasons it's good is because people that are using it can input from their location whether they can see an aurora or not. So you get a live developing map. It's all X's in here. You get live developing map as to whether you can see the aurora or not. And that allows you to then think about going out to your favorite aurora watching site and being able to take a picture or not. Anyway, enough of this. Here are some other pictures that were taken. This is from Ian Hall of North Ronaldsay Astronomy Group. You can see the colours here. You can see the green. You can actually see some rays. You see some colours. Look at that. Look at that. There's the purples and pinks and some more dancing rays and the whole depth of colour that you get in aurora. Absolutely wonderful. And here we are, Sue Shackleton from North Ronaldsay Astronomy Group, who is now also a fully fledged member of Highlands Astronomical Society. Welcome, Sue. I'm pretty sure I saw you on the participant list, so welcome to the club. Look at these rays. That is a fantastic picture from Tingwall in Orkney. Here's another one. And another one. Just wonderful pictures and just a lovely pastel shade of green. And now over to our very own Dave Davidson. Our monthly club meetings would not be the same without Dave's moon pictures. This is an absolutely wonderful one of a thin crescent, a new moon showing Mare Crisium. That's a wonderful, wonderful picture. And look at this one. We've called this one That's Relief because the relief is just stupendous. You have Mons Hadley down here, the crater Archimedes, Aristidus, and Autocyclus. You have the Alpine Valley, the Vallis Alpus. That's just a great picture. Great picture, Dave. It almost feels like 3D, to be honest. And these two pictures, they were taken in the daytime in January, in the afternoon of the 23rd of January, so not that long ago. And you can see the Mare Imbrium, the crater Plato, and Copernicus. And there's Copernicus in just a little more detail. And another one from Dave, taken on the same day. This was taken in the afternoon of the 23rd of January. And you can see it's a pale, watery moon against a blue sky. Many people don't realise that you can see the moon during the day, but you can observe it quite easily with a telescope. You can take camera pictures of it. So go out and have a look if you've got a reasonably clear day and the moon is at a decent altitude. Now here's some more of Dave's stuff. Deep sky stuff. We've got the Crab Nebula, a supernova remnant in Taurus, and a wonderful one here of the Flame Nebula. If you look closely, you can see the Horsehead Nebula. And of course, there has to be a man-made satellite just crossing the image just to spoil it a little bit. But that's the way of the world, isn't it? Now, Dave also managed to capture the conjunction of Mars with the planet Uranus on the 19th of January. Also, well, I think we already know this, Dave is a weather optimist. Dave was dying to get his sunspots, to get some sun pictures. And here you can see his setup. The sun obviously wasn't too far over the fence, judging by the shadow here on the wall, but Dave got his picture. There you go. Dave has captured the first Highlands Astronomical Society sunspots of 2021. So well done, Dave. I'm now going to have to look out my solar scope and start trying to take some pictures. I think Anthony's on. I'm sure, Anthony, that you will be doing exactly the same. And now we go over to the Isle of Harris and Stornoway Astronomical Society. And here we have Mark Waugh, who is on a steep and very fast learning curve in astrophotography. Mark has been producing some wonderful work. We actually showed a picture, I think it was last month, where he was called Mark, but we now realise that that was his Facebook handle and that was only a stutter. His real name is Mark Waugh. Mark, welcome. I know you're definitely watching us tonight, and we're just going to enjoy some of your pictures. This one is of the Pleiades, the Seven Sisters, Subaru, or M45, whatever name you want to call it. And this is a reflection nebula where the stars are reflecting the particles of dust, so you get this blue-green effect. Mark has captured M31 and its sister galaxies on the 14th of January. And even in the short time of 2.5 weeks, his imaging and process capability has grown to produce this much improved image of M31. But they're both fantastic images, Mark. Absolutely fantastic indeed. And this, for me, is a stunner. You have no doubt that this is the Horsehead Nebula. When I was a student, or even in my 30s, this would have been impossible to be done by an amateur astronomer or astrophotographer. It is a brilliant, brilliant picture of the Horsehead Nebula and of the Flame Nebula. There is the star Altenac, and that's the star that's actually lighting up some of the nebula features that you're seeing in this picture. And of course, you can't take pictures in that area without taking one of the Great Orion Nebula itself. This was taken on the 19th of January, and this really does show some fantastic cloud structure, some lovely wisps. I think this was also only a couple of frames stuck together, and it was processed, and it's really, really wonderful cloud structures that have come out. This one, I think Mark said this was about 60 frames stacked together, and you've got much more of the subtle gas cloud that's throughout this much wider area. Used different processing techniques to bring out the core as well. The stars that light up this nebula, it is just superb. Thank you for doing this, Mark, and we look forward to more of these type of pictures. And have we got something special? Well, this is the Rosette Nebula. This is one of the images that I am desperate to capture. Pauline, you mentioned this one in your talk last month in your targets. Isn't it just great? It's a big hydrogen dust cloud. It's been lit up by a concentration of very, very big, bright hot stars in the middle. You can see the rectangular shape that Pauline referred to last month. And that's the way you actually find the area if you're hunting it down in a telescope. It's a great picture. Mark, you've set the standard. You've set the bar. I will definitely be having a go for this in the next few weeks. And I think the last of Mark's pictures, the Eastern Veil Nebula, he's got it like a smile here to cheer us up in these difficult COVID times. And now we go down to Surrey, where a man called Andrew Jenkins, and yes, he is a relation to Paul, he's Paul's nephew, and this is a brilliant hydrogen alpha picture of the Great Orion Nebula. It's really brought out the wispy infrastructure of the nebula, of the cloud. I think it's just great that Highlands Astronomical Society has such an impact on people so far south in the British Isles. But I'm going to end with my favourite astro pic this month. This image is just something else. The full moon was called the Wolf Moon, but Sue Shackleton got this, and I think we're going to have to rename it the Goose Moon. For all of you who don't know, Sue is also a goose trainer, and she trained one of her flock to fly in front of the moon so she could capture this picture. I'm only joking, it's purely fortuitous, but isn't it a great picture? I think Sue submitted it to BBC Scotland News for their weekly photograph carousel, so hopefully it gets picked up and published. But Sue, a stunning, stunning picture. That's going to be the desktop of quite a few people, I think. So guys, that's it for me this month. Just to thank you for watching. Clear skies and keep looking up. Paul, back to your good self.
Okay, guys, thank you very much indeed. I'll close the meeting. Hopefully, you'll all feel that this has been a successful evening. My thanks to all of you who have worked so hard to bring this webinar about. It's much appreciated, all of you, and particularly Rich and Mick from Sigma, who host us so well each time. A final reminder then before I close this webinar, if you would like to join our follow-on meeting for a blether, click on the chat link at the bottom, the chat icon at the bottom of your Zoom screen. And once the chat boxes come up, click on the link that Rich has put there, and you'll be pitched out of this webinar and into the blether meeting. It might take a minute or two for Rich to open it up, but hopefully we shall see you then. For those of you not joining us there, good night, and thank you for watching.